So this is Note-Taking Guide 5.8. This is the last note-taking guide in Chapter 5. It's been a long chapter of functions. We've learned how to do a lot of things with them, and today we're going to kind of wrap it up, make sure we can remember what we did, and do a couple of story problems. So, all right, so let's get going. On this first one it says to identify whether or not it's linear, exponential, or neither. So I want to remind you how we could tell that something was linear. Well, what we did was we checked the pattern. If it was linear, the pattern changed by addition. It was arithmetic, and it changed by addition. If it was exponential, or if it was, then the pattern on the change was multiplication by a number. So we're just going to look to see if we think these things are multiplying, or if we think that they're going to grow by addition. So it says a savings account that starts with $4,500 receives a deposit of $400 per month. So the question is when we put $400 per month in, are we multiplying $400 or are we adding $400? We're definitely adding $400, and because we're adding $400, it's going to be linear. So the reason is that we are adding. That's how we can explain that it's going to be linear. All right, the next one says, Tina owns 4 rabbits. She expects the number of rabbits she has to double each year. Double actually means to times by 2. So this is a dead giveaway of what this one's going to be. That's going to be exponential, because anytime we multiply for our pattern, it's an exponential function. All right, this next one is actually in a table of values. So remember, we're looking at y values, and if they have the same kind of pattern of change with either addition or multiplication. Well, how do we get from 5 to 7? We add 2. How do we get from 7 to 9? We add 2. 9 to 11, add 2. And 11 to 13, add 2. Because of this addition right here, it's going to be linear. And the explanation, again, is that we are adding on our pattern there. All right, next one, again, looking at those y values, checking out that pattern. How do I get from 15 to 30? I either add 15 or times by 2, but I can see that it's times by 2 to get from 30 to 60. I times by 2 to get to 120, and then times by 2 again to get to 240. Because I'm timesing, it's exponential, and that's, again, the reason, or our explanation, is that we're timesing by 2. All right, this last example is a story problem. It says, after graduation, you are offered 2 jobs. Cedar Grove Associates offers to start you at $30,000 with a 6% increase per year. Maple Grove Associates offers to start you at $40,000 with a $1,200 raise per year. Compare to the 2 jobs by completing the table below and then answer the questions. Okay, so let's start with Cedar Grove. Cedar Grove starts us at $30,000. These might be way too small to write those numbers in. It's hard on the iPad because I have to write with my finger, and then it's kind of like a scribble instead of like a... Let's see if I can get the numbers in there. So that we start out with 30,000, and then it says we get a 6% increase every time. So what we're going to do is we're going to times by 0.06, because that would be a 6% increase. So let's take that 30,000 and then timesing by 0.06 would give us the increase. I want the total though. So I really want 1.06, because that would be 100% of what I have plus an extra 6%. So I'm going to times by 1.06, and that's going to give me $31,800. Then I'm going to take that number and I'm going to times it by 1.06. And that will give me the next number. So 33,708. Then times that by 1.06. And I get 35,730. And I'm going to leave the change off just for the fact that I can't fit them in my boxes. Times by 1.06. So again, this is going to be 37,874 and some change, but again, I'm leaving the change off. So times again by 1.06 or 40146.76. Oh yeah, leaving off the change because it's too messy. 46. Several more to go here. Timesing that one by 1.06, and I get 42,555. Times that by 1.06, 45108. Times by 1.06, 47815. Doing it again. 50684. And then one more time. All right. So there's my numbers for that value. Now I want to point out that we know that this one is exponential. The green one is going to be exponential because we multiplied by a number. It was a really small number, 6%, but we did multiply by a number. Okay, Maple Grove starts us out with $40,000 a year. And then we're going to add $1,200 to it. So we know that this one's going to be linear or arithmetic. But we're going to add $1,200 to that every year. So 40,000 plus 1,200 is 41,200 plus 1,200, 42,400 plus 1,200, 42,400. I think I just wrote that one twice. I did. 43,600. 44,800. 46,000. 47,200. 48,400, 49,600, 50,800, 52,000, 53,200. All right, that was a lot of numbers to fill into this table to be able to answer the questions about it. But let's see if we can answer the questions. So it says, Cedar Grove models what type of function? Well, we already said Cedar Grove was exponential because it was multiplying by a number. B says Maple Grove models what type of function? Well, we already said that was linear because it was adding a number. C says if you plan on moving to a different state in 5 years, which company would be the better option for you to choose? So if we're going to only work for a company for 5 years, which would be to right here, it seems to me that Maple Grove would have the better income for those first 5 years. So we would want to choose Maple Grove for those first 5 years if we only planned on working for 5 years. D says if your plans change and you don't move, which company would be the better option to choose as a long-term career? Well, as a long-term career, I mean, come look at 12 years out. 12 years out, the top one that we're multiplying by, even though we were multiplying by such a small number, is growing significantly faster than the other one at this point. So it's definitely got to be Cedar Grove if you're going to stay for an extended amount of time with that career. So that just kind of shows you how exponential and linear functions grow at different rates. Sometimes a linear function could be good for the first little while, but in the long run, exponential functions usually will I don't know what word I'm looking for, outvalue them in the end. So, all right, anyways, if you have any questions, come and see me. Thanks for watching. Good luck with your homework.